So our next speaker is Marius Ionescu, and he's going to tell us about wavelets via influence.
Thank you so very much for the introduction, and of course I want to start by thanking the organizer for organizing this wonderful event. I will be here this week, but it has been a really great, and especially I want to thank for helping me so graciously with all the tasks, extra tasks that I ask of them to make my trip here possible. So this presentation is based on the recent work with Paul Muley. We have been working on this project for a very long time, longer than we thought, and I'll try to explain as we go why. And it's about obtaining, wavelets using groupoid techniques and groupoid representations. Before giving an overview, let me actually, for those of you who are not familiar with wavelets, I'm going to give one slide introduction, but actually before that, I want to say that Paul and I, we dedicated our paper to the memory of in Rayburn, because in particular, his work with many photos, Nadia in particular, has been really influential and motivational for us. So as I said, for those of you who are not familiar with wavelets, let me just give a one slide introduction to the concept that we are trying to study from a grouping perspective, and namely the so-called multi-resolution analysis that was introduced by Malat in 1987. And what that an MRI, so multi-resolution analysis, an MRI, what it means is just a sequence of closed subspaces of L2 of R, that it's increasing sequence. The union is dense, the intersection consists on just the zero vector, and then property for what it really means from our perspective, how probably you can read it, is that there is a unitary floating around that moves the one space to another, and properties 5 and 6, what they mean that unitary interacts in a nice way with local homeomorphism. It goes to sigma to z square. Right, so again, the details are not relevant, but the fact that the existence of the local homeomorphism and the unitary led to many people in operator algebra, operator theory, to work and try to build these things. But before, might be wonder, does such a thing even exist? And Malat showed that yes, they do. It depends on a choice of a function defined on the torus that satisfies some properties, and it's called a filter. And once you have that filter that satisfies the right property, he defined the so-called scaling function. Using the scaling function, we did some heavy Fourier analysis, you proved this. But as I said, on the operator algebras perspective, probably the first paper, at least that I'm aware of, was Bratelli and Jorgensen, which they realized that, the fact that you have the local homomorphism z equal to z square, you can extend it to other local homomorphisms, and you can obtain MRIs or generalized MRIs in other ways, and there's been a lot of work and improving this. And in particular, I want to highlight a paper by Nadia and in Rayburn, which they prove Malat theorem very neatly using some inductive limit of Hilbert spaces. From our perspective, so all these constructions that we find in the literature, they have similar flavor, and in particular, most of the constructions start by once you pick the filter that I mentioned, and I'm going to define later, one can build an isometry on some Hilbert space L2, then extend it to a unitary extension of that isometry, and so with a bit more magic, you get either MRIs or generalized MRIs, and by generalized MRIs, I mean maybe not necessarily in L2 of R, but some other Hilbert space. But again, Paul and I for a long time agree that using groupoids, particularly the Diacono-Renault groupoid, since we have a local homomorphism, should help extend and unify some of the theory, but also kind of put an order which choices along the way are intrinsic to the system and which depend on just the choice of a specific representation. So in our work, we use, as I said, the Diacono-Renault groupoid, and some pullbacks of the Jacob-Renault groupoids, and we induce the representations to obtain the similar objects. But as I said, so we will start with the Jacob-Renault groupoid, but we'll build out of it a new groupoid. So let me present that construction in a more general setting. It has been in the literature, so this maybe with other names, some creations or blow-ups. But the starting, so we have a locally compact Hausdorff groupoid with a Hart system. And the second ingredient that we need is a surjective open continuous map from another locally compact space onto the unit space of the groupoid. And once we have this ingredient, we can form what we call, based on a suggestion by Jean Renaud, the pullback of G via pi as just the fiber, basically product of YGY, so fiber over the map pi R and pi S, with the natural groupoid operations. And notice that the unit space of the new one will be, of the new groupoid will be Y. Now, I know for some people in this audience, believe that the tau groupoids are the right ones to work. But here, even if we start with an étal groupoid, as we do, the Renault groupoid is étal, we're immediately led to leave the étal word because this GY will be an étal groupoid only if the map pi is a local homeomorphism itself, and in our case, it's not. So we think, and that was actually one of the reasons why our work took a bit longer. Initially, we thought we can do everything within étal words, and it turned out not to be the case. But nevertheless, what is important about this groupoid GY, and it is equivalent in the sense of Muller-Renaud-Williams with G. So then by the work of Williams, since G has a Hart system, GY must have a Hart system. And in this situation, we can actually give a nice formula. So all we need is a full pi system of measure of Y. What it means, nu is actually a family of measures indexed by X, and the support of each nu X is equal to the fiber pi inverse of X. And then we can integrate the nu and lambda again. Don't worry if you don't want to follow the formula. So many of my formulas in the slides, I put them just to indicate they are concrete and actually we can do computations. But don't worry if you don't. But we have a Hart system on GY. And of course, by the general theory, C-star algebra of GY is Morita equivalent to C-star algebra of G. So we could induce representations, and an equivalence will be given by Y star G, so the fiber product Y star G. However, the second reason why our work took a little bit longer to finish was that we needed to induce representation when we have system of measure of Y that are not necessarily full. And dealing with that, we managed to deal with that when we finally understood the work of Holkar, and they are not fully the following things. So these measures, this subsystem will be fixed, and what we are going to do, we are going to multiply with the function, and it has some zeros. That means we punch holes into it, and namely, what we consider again, we consider a function d, and we multiply by d to. It doesn't have to be zero, but if it's zero, it cannot have too many zeros. It cannot kill a full fiber. So the whole point, we still need to obtain a proper system of measures on this equivalence between G, Y, and G. But since the system of measure now might not be full, we don't obtain in general the equivalence or implementivity by module. We obtain something that Holkar calls topological correspondence between G, Y, and G. Satisfy these three properties. And let me again highlight from the third one that this is extra function that he calls a joining function that has this forming for our case, that kind of is needed for the equivariance, which also is needed when we define a left action. Because once we have this system of measure, we can complete the continuous functions on Z, compactly supported continuous function of Z, to define a C-star correspondence from C-star of GY to C-star of G. And for the left action of C-star of GY, we need a joining function. And therefore, again, we can induce the C-star correspondence that we obtain. It might not be full, but nevertheless, we can use Riffle's theory to induce the representations. But again, since we want our computations to be concrete, we want to induce from groupoid level to groupoid level. So let me design here. So by using work by Renault, so a representation of a groupoid consists of a quasi-variant measure on the unit space, a Hilbert bundle on the over the unit space, and some homomorphism of G into the corresponding groupoid given by the Hilbert bundle that respect the laws of G. And once you have such an object, you can integrate to obtain a representation of C star of G, then induce it via equal to C star of GY. But then by the Renault theorem, you disintegrate it and obtain a representation of the groupoid GY. And the point here is we have concrete formula, so we have obtained the new measure that is known Y, quasi-invariant measure, a new Hilbert bundle, an induced representation, and the system, the function D that punches hole, it's used in the definition of the induced measure, but again, it's natural and easy to compute in concrete cases. The new Hilbert bundle and the induced action actually again are natural and easy, and they don't depend on that. So we use this later on to actually in concrete and they might look scary, but in concrete examples actually you can put you can do it. So let me, as I said, now come back to our setup. So we consider a subjective local homeomorphism on a compact space. We take the Diagonal groupoid that has been mentioned many times in these talks. So let me not define it, but I want to point out for that some useful Copen sets in the Diagonal groupoid. So if you fix N and M positive, R and M are all elements in the groupoid that for each sigma N of X equals sigma M of Y. And when N and M equals 0, you just get a unit space. When N equals M in general, you get the equivalence relation, and they are form an increasing sequence of equivalence relations. And when N is 1 and M is 0, this is just basically the graph of sigma, and the indicative function of that will be scalar proper. They will provide us the isometries that we need. So that's the starting groupoid. Now we need the space Y and the projection. So the space Y will be what we call the projective limit, so the set of infinite sequences, such that each component is the image under sigma of the next one, and the project chi is just the projection onto the first component. And then we'll pull back as we did before, then we call the pull back G infinity of X sigma, or just G infinity. Sometimes I use just G and G infinity. So we have again G, we have Y, we have pi, we pull back, and then we need a pi system of measure on X infinity. And these are obtained by looking at basically left inverses of the star homomorphism composing with sigma. And these are given by not zero function, unital. If I plug in the identical function 1 here, I want to get 1, then the function size called a potential. And once we have this, can build in a natural way a system of measure on X infinity that is full, and this will give us the hard system on the Caesar algebra of G infinity. But as I said, we want to potentially punch holes or change this system to when we induce representations, and this is where, from our perspective, the filters come into play. So far again, we have as choice the space, the local homomorphism, and now we have a filter that we choose it in a way that interacts well with a quasi-variant measure. And now we can choose the filter that depends on psi function, such that when you look at the square of M in absolute value, plugging in the transfer operator on the previous slide, you always get 1. So it's a unit for the transfer operator. And that they always exist. And connecting with the previous notation, so the D function, it's basically M of X squared. And I'm introducing a new notation here. U will be very important. Square root of X, M of X, so basically taking square roots in there, that's the square. And D, which is square root of this function, basically D is just this guy. And this equation implies that D is also a potential for a transfer operator, but it might not be full. But regardless, this function U defines an isometry that lives in the sister algebra of the diagonal groupoid. So by taking the indicator function of the set R10, so the graph of sigma, and multiply with U of X only. And of course, as I said, D defines the system of measure on X infinity. Might not be full, but we get the sister correspondence in the sense of using Hawker's theory. So we can induce that. So the next step is we want to find the unitary extension of this isometry, and of course, this will be on the sister correspondent that's obtained by completing CC of X infinity star G, and I'm going to call it also X infinity, that completion. And again, this might look intimidating, but the point is that it's concrete and we can apply representation to it and get the formulas that we want. So it's a concrete one, and the function U comes here, and this is a unitary extension of the isometry that I defined on the previous slide, and it's one ingredient that we need in our form of the definition here. For the second one, again, I taken another set R11, so equivalent sigma of X equals sigma of Y, that using the diagonal groupoid, but it can be the sister algebra of the diagonal groupoid. It can be embedded into the sister algebra of the pool G infinity, and that acts on the left on this sister correspondence, and this will define a projection, and then we define a sequence of projection by moving around this E by this unitary. And we call this the proto-multi-relational analysis determined by this parameter X, sigma, psi, and M, because they are the source of all the pretty much the multi-relational analysis that we know in the literature in the following sense. So the sequence of projections is an increasing sequence. They fill up the whole sister correspondence. The unitary moves the things around. So again, these are properties very much, and the diagonal groupoid interacts with the unitary in a nice way. So pretty much all the properties of the multi-relational analysis, with one notable exception, that we don't know the intersection is zero, and we don't need it because we'll get there when we apply specific representation. So we need things to happen in the Hilbert space. This lives in the sister correspondence. So we need to apply representation, and under some conditions, we obtain that for free. Instead of describing those conditions, let me give a class of examples in which we obtain not only the real MRAs, not generalized MRAs, and that's all. We start with a continuous function, the least one, periodic of period one, so the integral from 0 to 1 phi of x dx is an integer, at least 2. Then this defines a local homeomorphism on the torus by basically sending a to the 2 pi x to e to the 2 pi integral 0 to x phi of t dt, and can be shown that this is an n-fold covering map of t. And in the next couple of slides, if you want to just keep in mind phi of t equals n, because then the integral is just an x, and so then the sigma of z equals e to the n, that's more than fine. But also I want to point out that the finite Blaschet products whose zeros are within the unit disk, restricted to the torus, they fall into our this category of examples. So it's quite a large. So again, the choices that we make, so the potential, we need a potential to define measures, and that's a natural one. It's 1 over phi of x that interacts nicely with the Lebesgue measure on the torus. And now this is, we pick a psi filter. And again, this is just to record the notation. U was this product and D was the square of U. And basically, this is our generalization of Malat's theorem to this general context. So if we have these three hypotheses, I will say in a moment a word about them, then we can define a scaling function from R to R, and scaling in the sense that it respects this property. And again, if you want to keep in mind phi of t equals n, this just means phi of nx equals u to the 2 pi x, so it's the usual n scaling property. And this scaling function belongs to L2 and satisfies this, what I call an orthogonality conditions. So what for us was, unexpected that this hypothesis basically are identical with Malat hypothesis that Malat had in his paper for sigma of z equals v squared. And the meaning of the first one, don't you recall, sigma is an n-to-1 map, so the preimage of one contains endpoints. The first condition says that the filter must vanish on all the points that are different than one, n minus one of them. The second condition says it can vanish only on those points. And the third one is a smoothness condition that we need because phi is defined as an infinite product, so just needed for the convergence. Okay, but once we have that, again, everything so far is still at the level of Caesar algebra. So now we move to the Hilbert spaces, so we pick representations, and to obtain the results in the literature, we just pick what we call the standard fundamental representation. So mu is the Lobeck measure because it interacts nicely with the transfer operator that we have. Basically, the Hilbert bundle is just a trivial one, T times C. The representation, just a trivial representation, I of z equals z. That's a representation of the diagonal groupoid. We apply the construction of inducing it to G infinity. And then one can show that there is, so then the induced representation acts on L2 of T infinity mu infinity, but using the scaling function, we can define an metric isomorphism from L2 of T infinity to L2 of R that intertwines the image of the unitary that we had before and his unitary in L2 of R. And again, if it looks intimidating, keep in mind if phi of x equals 2, this is just 2x, so this is exactly what Malat had in his theorem. And the proof of this is once we had the existence of the scaling function, we basically almost take word by word the proof of Nadia and Yin from that paper on with the induced Hilbert spaces to define more modulo some complication, but that's basically almost word by word to define R. And to sum up, sorry, this is the last slide. To sum up, so we obtain a multi-resolution analysis on L2 of R when we move everything, so we have the proto multi-resolution analysis in the Hilbert space, in the Hilbert Caesar correspondence. We apply the induced representation that will be in L2 of T infinity. We move everything with the isometry R, we get in L2 of R, and here we obtain basically a multi-resolution analysis, so get the property that the intersection is zero also. And again, the scaling is not, doesn't have to be 2 or n scaling. It can be, it's what we call a non-constant scale. Thank you so much, and I apologize for going over and here a bit of bibliography again, in particular some of the papers by Nadia and Reber and other quotes that we use. Thank you so much.
Are there any questions?
Just to clarify, so this direct limit construction that we had, so this is really what the induced representation now captures, in a sense.
Yes. Yes, so the induced representation can be described on that. So you can go straight from G to G infinity, but there are also a sequence of intermediary groupoids you can get there, and you can induce and get an untitled limit of Hilbert spaces that give your construction basically.
And that convergence, that very delicate point of convergence, that's somehow subsumed in your choice of
So no, once we have, so these conditions are necessary for the convergence. Once we have it doesn't have to be zero anywhere. Once we have such a filter and we have a D, the measure on infinity exists, and that construction just works.
Other questions? Should we thank the speaker again?